Mars memory usage is almost similar to what MIPS suggest. Okay, so this your right hand side picture is actually taken from your textbook, Hennessy Patterson's textbook, uh, that white page or green page depending on what revision you are looking at. It talks about this memory usage suggestion and different power of values of stack pointer, global pointer, PC, etc. The Mars memory usage, you can actually, I'll show you later how this map we can see from in the Mars IDE. But this is I cut paste from that part. I bring up that Mars memory usage and their memory model, and try to compare between them. So we'll see they're mostly same except couple of points. Okay, we'll highlight that too. First of all, the higher part from 7 all F, like 7F, FFFF, etc., that 32 bit. After that, it's about kernel and MMIO. Remember memory mapped IO? So that's what the MMIO stands for. So IDE, I remember IDE, and this Mars provides you system call like function like syscall, like for printing string, printing integer, etc., and scanning from the keyboard, taking the value from the keyboard. Those kind of little operating system like functionality it gives you in your assembly program. This part, in fact, is actually part of their memory, like the memory they're presenting to the simulation environment of the MIPS, right? So remember, this memory is also simulated. The processor itself is also simulated, so they're kind of staying in the virtual world, but nonetheless, it reflects the real operation scenarios, right? So this upper half is for the kernel and for those memory mapped IOs, and then lower part is mostly what we talked about in the last slide. So your stack base address, which is like MIPS points stack pointer to FFFFFFC, that is your stack base address for your stack usage of the memory. Now the higher address, if you see the 7FFFFF, they both are defined, that location defined as user space high address, means user are not supposed to go beyond that. And I believe if you try to do it, your assembler will complain about this somewhat, but it might not. I may be wrong. Please do that experiment yourself and just convince yourself what it does. Okay. Then also data segment limit address is also defined at this address 7FFFFFF. So these are the highest part as a user program we can access or we should access, and base pointer address is actually pointing to what MIPS suggests as a power up address of the stack pointer. Now in the Mars, your stack pointer, if you assemble and look at before you start your program, if you look at the stack pointer content, it actually contains something like 7FFF EFFC instead of FFFC. Okay, so your stack pointer is somewhere below your stack base address. Okay, stack base address. So I'm entirely not sure why someone would go and do this, like what is the reason Mars decided to have a stack pointer start at a different address than what MIPS is suggesting. But one reason maybe is that the upper half than this EFFFC, the upper part, is if someone want to use it as passing argument to the main program. Okay, passing argument you store. Remember, like if you programming C++, I think it is in the Java as well. You are writing your main routine, and in the main routine you can actually pass arguments like this int. In C++, it is basically number of arguments and an array like a void pointer arg. It's called an argv and argc, right? That too. This argv is an array of argument information, right, which can stay on top on the higher address than the stack pointer pointing as EFFFC. So I believe Mars has created that space for us in order to implement this main program, argument passing into the main program. We can store the all the argument values in the needed for the main program calling at that point and access them from that point. However, that is purely my guess, okay, my educated guess, and that's probable cause why they wanted to start at 7FFF EFFC. Okay. Nonetheless, the point is Mars start as a different point than what MIPS suggests to do. All right. Then we have the data segment base address, and which is also extern base address, which is starting at 100,000 hex. Okay. So I think this is basically what we do at. Now let's look at this static data part, like this data segment base address, and also it act as a extern base address. Extern we'll see later in when we are trying to deal with the global variables, but just keep in mind that both extern base address and data segment base address, they're the same address value, and it's pointing to 100,000, and it's similar to what also MIPS memory usage suggests. Your global pointer is pointing, as MIPS suggests, to 100,080,000. Okay, hex. So that's one thing. Now there is a little bit different in terms of dynamic data allocation, like heap. What we call is a heap. Okay, so heap grows up, and from MIPS memory usage, your static data is starting from 100,000 till 100,080,000, right? And after that, heap can start allocating memory, like for any new operation, new malloc, like in C, especially not C++, C it is malloc, which stands for memory allocation. In C++, Java, it is new, like new object allocation. That starts from that point. But Mars is a little bit different. Okay, Mars local data locations, okay, starts from the base address, that's fine, which is pointed by MIPS, but it spans beyond 100,080,000. It spans up till 1000 FFFF. Okay, so all your local data, like you're storing bytes, storing strings, storing values, all these local data and global data, this is reserved for your global variables. Okay, Mars local data location, okay, is reserved for global variable. So what it means really is that data section you are setting up, or extern, we'll see later, like any external variable we are thinking of that is incoming from other modules, will be spanning from this entire 64 kilobyte of area. Okay, starting from 100,080,000 Now, what is the advantage of that? Like, if you keep the global pointer GP fixed at that location of 10008000, then you can access this entire 64-bit space as shown, this address space relative to this global pointer, okay, with 16-bit relative index, okay. So 16-bit, like unsigned, it actually 64k, okay. By unsigned value you can make 64k different values out of it, and of course if you go for the 2's complement form of the 16-bit, it's basically plus 32k to minus 32k. So if you actually go minus 32k from the global pointer location, you hit the boundary, lower boundary of this global variable position, and if you do add plus 32k, you will hit the upper bound, which is 1000ff of the global variable. Okay, this is your local data goes into the memory of the Mars simulated MIPS, which is little bit different than your normal MIPS usage, memory usage suggestion. All right. So that means in the Mars, your data starts like dynamically allocated data, like heap part start after 1000FFFF, which is basically 10010000, that address. Okay, from that address your heap start growing. And text base address is pointed by the program counter, which is same as in the Mars on and the MIPS usage suggestion, which is 00400000. So that's your basically your Mars memory model, which is very much similar to what MIPS memory usage suggestion said. One difference is your stack pointer power up address, which is differ from what MIPS suggested. For some reason, I have given you a plausible cause of that. And other part is the usage of the static data. The static and data and global variables, all those things spans beyond what MIPS suggested. So it actually gives you more space for constants and global data and so on and so forth. So your dynamic data space is much less in this case for Mars.